Okay, final FRQ in this packet from 2003. It is the first question. This one, I will go ahead and warn you, is a little bit different because it deals a lot more with numbers than we are used to. Here we go. The 100 kilogram box shown above is being pulled along the x-axis by a student. The box slides across a rough surface and its position x varies with time t according to the equation x equals 0.5 t cubed plus 2t, where x is metered and t is in seconds. The first thing I am absolutely going to do when I see an x equals equation with time in it, I'm going to go ahead and take derivatives. So 0.5 t cubed plus 2t. The velocity, 3 comes down. 3 times 0.5 is 1.5. T squared plus 2. The t has a 1, it goes down. We're good. And our acceleration then, the 2 comes down. 2.5 is 3t. 2 goes away. I don't know off the top of my head, because I haven't read it yet, if I need these, but I probably will. A, determine the speed of the box at time t equals 0. Look at that. We already need the velocity. So we're looking at velocity when time equals 0. So that'd be 1.5 times 0 cubed plus 2. Guess what? 2 meters per second. We already needed it. Again, if you get an equation for position with a time as the variable, go ahead and derive, find velocity, find acceleration. If you get an acceleration equation with time as a variable, integrate to find velocity or position. Determine the following as functions of time t. So in these places, we want the velocity with the only variable being t. All right, kinetic energy. Let's go to a different color. K equals 1/2 mv squared. Do we know the mass? Yes, it's 100 kilograms. What's half 100 kilograms? It's m over 2, right? 1/2 m. So it'd be 50 times our velocity, 1.5 t squared plus 2 squared. You do not have to multiply that out. You could FOIL it all day long, but this is good enough. You've got a function with respect to t. Okay, the net force acting on the box. Well, we know force equals ma. Remember when I told you to go ahead and derive for a? We've got it. Our mass is 100 kilograms. Our acceleration is 3t. That's very simple. 300t is our force. Questions, comments, concerns? You can't ask them because I'm not there. Okay. Number 3, I. Power being delivered to the box. You might initially think that power equals work over time, and work is force times distance over time. That's only true if we have a constant distance. We do not have a constant distance, so we can't use that equation. What we can use, and I believe this is on your blue card, double check, it's just in my brain so I remember it, full power equals force times velocity. This works if we have a varying velocity. All right, so our force was 300t. Our velocity is 1.5 t squared plus 2. Since we have two things multiplied together like this, let's go ahead and multiply them all the way out. 300t times 1.5 t squared. What's t cubed? 1.5 of 3 is 450 t cubed plus 2 times 300 is 600t. There is our power with respect to time. It then says calculate the net work done on the box in the interval of t equals 0 to 2 seconds. This is where you hopefully remember that work is equal to the change in kinetic energy. It's one of the big ideas. Hopefully you remember me teaching that. So that would be initially to finally, and I'm going to write it out the way I have it, our kinetic energy, I'm going to scoot it down, was 50 times 1.5 times t squared. T is final 2 squared plus 2, all of that squared, minus 50 times 1.5 times 0 squared, nope, sorry, just 0, plus 2 squared, like that. This doesn't go away because 1.5 times 0 goes away, but it's 2 squared. 2 squared is 4. 4 times 50 is 200. So that whole number here is 200. 2 squared is 4. 1.5 times 4 is 6. 6 plus 2 is 8. 8 squared is 64. 64 times 50 is a number. Put it into your calculator because that's what I did anyways. 3,000 joules. That's what you should get. And then finally, this one's a quick one. D, indicate below whether the work done on the box by the student in the interval of t equals 0 to t equals 2 seconds would be greater than, less than, or equal to the answer in part C. Okay, so this is a little bit confusing because we wanted to know the net work done on the box in the interval of t equals 0 to 2 seconds. That is the net work. That is, when all is said and done, how much work was actually done. But this is asking how much work the student had to do to pull it. Remember, we had a student pulling this to begin with. Nowhere in this problem does it tell us that mu equals 0. Pulled along the x-axis, slide across a rough surface. As a matter of fact, it doesn't even say mu equals 0. It says rough surface, which tells us we have friction. So the work that the student does has to be greater. Justify your answer. Since the surface is rough, he had to, and I'm going to use a big word here, overcome friction. And that is good enough. All right. If I don't see you before Monday, go kick some butt. Take your time. Do what you can do. Don't stress about what you cannot. Go Pack.